Assalamu alaikum and hello everyone. Welcome to this channel by Mimo. You are watching the first video of our new series which is about electrocardiogram or commonly known as ECG. This is a very crucial and complex topic to learn, so I will try to go a bit slow on this one. Before we jump straight to the topic of this video, let's look at the overview of this new series. To develop our basic understanding of ECG, we are going to learn some selected topics from anatomy and physiology, which I think are crucial before we even start analyzing our ECG strip. Those topics are the conduction system of the heart and cellular electrophysiology. Then we will start analyzing the waves and straight lines on ECG strip and get to know our ECG leads. Later, when we have grasped the basic knowledge, we can start learning about common cardiac and non-cardiac disorders that make useful of this diagnostic equipment. In this video, we are going to learn about cellular electrophysiology. Before we start, the references and credit for this video goes to Textbook of Medical Physiology by Guyton and Hall, Human Illustrated Physiology by Nouriah Muhammad Noor, and the only EKG book you'll need by Malcolm S. Thaler. First and foremost, to make sense of ECG, you definitely need to know about cellular electrophysiology, because what you are seeing on the ECG is really a repeating cycle of the cardiac cells depolarizing and repolarizing. In its resting state, a cardiac myocyte cell is electrically polarized, that is, the intracellular is negatively charged and extracellular is positively charged. You may wonder, why is it polarized in resting state? Shouldn't all things balance at rest? And why aren't the electrical charge evenly distributed so that it will be neutral? Well, let's revise some basic physics. Take a book, for example, and let it go from a height above the floor. We would expect that the book will fall. Why? Well, we will say that it is because gravity exists. But really, gravity is a degree of acceleration towards the center of the earth. When the book is falling, it is going about at an acceleration along with its mass. A combination of these two, you will get a force, and this force going downward is also known as weight. In the second situation, we have a book on a table. Nothing is moving and everything is at rest. But is there any force at play here? Well, of course there is, because you can't eliminate gravity. So there is still weight to the book, shown as a force going downward here. Now, according to Isaac Newton's third law of motion, it states that for every action there is an equal but opposite reaction. So from this formula, we can say that the book is not falling simply because there is an equal counterforce. And this force comes from the table mechanical strength, able to hold the weight of the book. But let's say if we put a 5 ton of stones on the same table, perhaps then we will see the table be crushed to the ground due to the massive weight that it simply cannot handle because of its limit. Now what about a cell at rest? There must be a force at play here as well, and they must balance each other out so that the net force is zero. A simple derivation from the formula, we can conclude that they also must be in opposite direction to each other, denoted by the symbol positive and negative here. So what are the forces at play? They are the concentration and electrical gradient. Let's try to explore them individually. We will first begin with concentration gradient. It occurs when a solid is more concentrated in one area than another. Due to the constant movements of atoms and molecules, substances will move from areas of higher concentration to lower concentration. In the first picture put up here on the left, there are 16 molecules on one side and none on the other. So there will be a driving force that will push these molecules to the empty area. The difference in gradient here are huge due to the both extremes. We can simply calculate the net force here is 16 from 16 minus 0. At the second picture, there are some already crossing to the other side, and at that freeze moment, the net gradient is 8, simply from 12 minus 4. And lastly, when the amount of molecules are equal on both sides, we'll say that the net gradient is 0. But does that mean no molecules are moving across the barrier? Well, there are still molecules moving, but the amount of molecule crossing from one side to another is equal to each other. Let's say if one crosses here, at the same moment another one will cross to the opposite as well. If 4 molecules cross, likewise another 4 cross to the opposite. Now that is concentration gradient at rest. But what about electrical gradient? Let's look at these 3 chambers with charges. In the first one, there are a lot of negatives inside and only 3 positives, so the net electrical gradient will still be negative. In the second chamber, we have the opposite where there are more positives than negatives, so you know that the net electrical gradient for this chamber is positive. While the last chamber are equal in charges, so zero net gradient, or in terms of charges, in neutral if I may. Now let's look at the combination of both the electrical and concentration gradient, or you may also call it the electrochemical gradient. We will try to make an example of a nerve cell. We know that our cells are full of proteins, nucleic acids, phospholipid bilayer, and lots of different ions, and the list go on. But those which matters to us for this topic are the potassium, sodium, and cellular proteins. To answer our question why our cells are at rest polarized, we need to build our understanding upon these 3 facts. First is that our plasma membrane are impermeable to proteins. They are located inside the cell and they are also negatively charged. Secondly is that we have sodium-potassium ATPase. Let's imagine him as our guy here. And remember, he works against the concentration gradient. That means our ATPase requires energy. He needs them in the form of ATP, hence his name ATPase. The product of his work will look roughly something like this. We have high amount of sodium ions in extracellular but low intracellular, and potassium ions which are high in intracellular and low extracellular. And the third is that at rest, potassium ions are most permeable. They go in and out of the cell as they please. We have a passive channel here, free access, but that is only to potassium. Does other ions have such a channel? Well, they have, but not as numerous, so they are less of an influence. In fact, these channels are so numerous that the permeability of potassium is 500-fold of that sodium at rest. But what about sodium? Well, they have their own channel as well, but unlike potassium, they need to pay to get an access in, like a toll. And the fee is negative 55 millivolt. Let's remember that number because we will come across it again. Now that we have that knowledge, we can talk about the first force, which is concentration gradient. Remember that proteins are impermeable and they are located intracellular, so there is no gradient to compare here regarding them. But there are differences in our ions. Sodium is high in extracellular and low intracellular, so the direction of force are towards into the cell. But since potassium is high intracellular and low extracellular, so the direction of force is the opposite, that is, in the direction out of the cell. Our second force is the electrical gradient. Inside the cell, all the charges here amount to negative. In this picture, I deliberately put 4 negative charges per cellular proteins to depict that so you can visually make sense of it, not that each necessarily have 4 negative charges. But regardless, since both sodium and potassium are positively charged, so their tendency or electrical gradient is to go into the cell since positive and negative attracts. Let's put our conclusion regarding both forces so that we can compare. We have concluded that the concentration gradient for potassium is directed out of the cell and sodium into the cell. And let's put a symbol to depict this. Remember that in the formula about force earlier, a negative only symbolizes opposing direction, not a value of negative. So we put the direction out of the cell as a minus and into the cell as a plus, or whichever you want because it don't matter. The point is potassium has a balancing force here, like the book on a table just now, where there is one force going down and one going up. But instead, here we have one going in and one going out. Sodium, on the other hand, has its both force at one side of the equation, so no force is directing it outwards. And we mentioned just now that potassium are most permeable because it has numerous free access channels unlike sodium. The thing is, even though sodium has a strong force going on here, because both their electrical gradient and concentration gradient are directed at the same direction, they cannot go into the cell as they please because they need to pay a toll. So they are like a potential force ready to explode into the cell here, like an arrow already drawn, awaiting release by a flick of a finger. Potassium otherwise are dynamic at rest. He is the force in action. Now I am going to introduce to you a new term here, that is the equilibrium potential, which means the membrane potential at which there is no net movement of ions. Let's take our potassium for example, since he is in charge here. So what does potassium equilibrium potential means? Simply the membrane potential at which there is no net movement of potassium ions. We know that there is a force pushing potassium in, that is the electrical gradient, and there is an opposite force pushing it out, that is the concentration gradient. Let's say we have 10 molecules of potassium ions moving in and out of the cell at any moment. 4 going out due to concentration gradient and 6 going in due to electrical gradient. Simple math would tell us that this amounts to net movement of 2. If there are 7 going out, 3 going in, the net movement is 4. But Thanos would not like this. In order to rest, he needs balance. So 5 potassiums going in and out at the same time. Now that is 0 net movement or potassium equilibrium potential. So at what potential these things happen? For potassium ions, 0 net movement occur at negative 94 millivolt. Interestingly, the resting membrane potential for a nerve cell is negative 90 millivolt. Kinda similar, right? Well, because it is not a coincidence. But where are the 4 millivolt difference? That is because we have not counted other dynamic ions at play here. We mentioned that sodium also have a passive channel, but very little. Well, maybe they are the little guy who contribute to this difference. But as you can see, the major power is contributed by potassium ions, so that's why he is our man at rest. In graphic representation, you may be familiar with this, the action potential graph for our nerve cell, and our resting membrane potential here is in red. We have talked about potassium, but when does our sodium has its part? Since we said earlier that it is a potential force waiting to be freed, right? So let's look at sodium equilibrium potential. So it is a membrane potential at which there is no net movement of sodium ions, and this thing happened at positive 66 millivolt. And likewise, it is no coincidence that the peak of our graph here, about 50 millivolt, is near to positive 66 millivolt. So how do we get to open the voltage-gated sodium channel? Well, first we need to get this cell to become less negative so that we can open the sodium-gated channel, and the fee the sodium has to pay to get in, that is negative 55 millivolt. Let's say a near adjacent neuronal cell is activated and it excites this cell, causing a movement of sodium ion into the cell. Let's call this the local potential. If there is enough sodium entry that the membrane reaches negative 55 millivolt, the voltage-gated sodium channel will open and allow massive sodium influx. But if there is not enough change in the millivolt, the sodium voltage-gated channel will not open. This is also called the all or none response. Now, our previously quote-unquote potential force ready to show off his power, a combination of both electrical and concentration gradient, pushes sodium into the cells, thus our cell becomes even less negative and more positive. This will reverse its original polarity, or simply called depolarization. At this moment, since sodium-gated channels are open, they are the most permeable ions. Its permeability at this stage is 5,000-fold to that of potassium. So it will try to achieve its sodium equilibrium potential so that he could rest just like potassium, simply to achieve no net movement at 66 millivolt. Let's look at the dynamic of the ion's concentration and electrical gradient, that is, during depolarization. Now, since we have inflow of sodium into the cell, a question you may want to ask is, does the direction of concentration gradient changes? We know absolutely that the concentration gradient will be affected as there are changes in amount of ions intracellularly and extracellularly. But the more important question is that does this affect its direction? Actually, it will not. Let us see why. Say we put a hypothetical value of our sodium and potassium concentration, both intra and extracellular during resting membrane potential. During depolarization, sodium rushes in, so some amount of extracellular sodium will enter into the cell and vice versa for potassium. Let's put a hypothetical value for that as well. As you can see, the shift of ions are not to an extreme that it will cause a change in the direction of concentration gradient. We have perhaps lots and lots of ATPases working to ensure that regardless the direction of concentration gradient across the membrane are maintained. Alright, now we have determined that the direction of concentration gradient do not change although depolarization occur. So potassium will still have a concentration gradient directed towards out of cell and sodium directed into the cell. But what about the electrical gradient? Since depolarization occur, now the net charges intracellular has become positive, whereas extracellular becomes negative. Now, since both sodium and potassium are positively charged, that means both ions are now pushed out of the cell. Sodium has two forces opposing each other, which will allow it to achieve its potential equilibrium, whereas potassium are being pushed out of the cell by both forces. So you can guess what happens if sodium-gated channels suddenly closed. Sodium stops coming in and potassium will be driven out of cell because there are two forces directing them outwards. But we have said that now its permeability is low during depolarization. So in order to overcome this, we have extra voltage-gated potassium channel as well. It opens as soon as the sodium channel closes. This will cause efflux of potassium out of cell. Combination of potassium efflux and limited sodium entry, the membrane will lose its positive charge rapidly until it repolarizes from positively charged to negatively charged, which is its original membrane potential. Voltage-gated potassium channel closes at a lower membrane potential. This will cause hyperpolarization. As the voltage-gated potassium channel closes, the sodium-potassium pump restores the resting membrane potential. So that's the action potential for nerve cell. So how different are our cardiac cell from nerve cell? Well, we can generally divide our cardiac cell into pacemaker and myocyte cells. And these two cells are different from each other in number of ways and have some similarity with our nerve cell as well. That is, in terms of ion channels and resting membrane potential. What we know about our nerve cell so far is that it has voltage-gated sodium channel, but there is no orange line here. It also has voltage-gated potassium channel. Its RMP is in straight line, or we can call it stable RMP. I'll explain that in a few seconds. It also has its RMP at negative 90 mV, which is relatively lower than cardiac pacemaker cell. Our cardiac pacemaker do not have sodium channel similar to that of the nerve cell, but it has voltage-gated L-calcium channel. It is also known as calcium-sodium channel or slow sodium channel simply because these calcium channel also allowed a limited amount of movement of sodium ion through its channel as well. Since we have slow sodium channel, then we also must have a fast sodium channel. That is the one that is in the nerve cell. It is also called the fast sodium channel. Later we will see why it is called as such. It also has voltage-gated potassium channel and slanted RMP or unstable RMP, and less negative RMP relatively at about negative 60 to negative 50 millivolt. Let's focus on our pacemaker cell first. As you can see, the nerve cell and cardiac myocyte cell both has purple lines, which denotes a local potential that occur due to the excitation from adjacent cell, which helps them to become less negative so that their voltage-gated sodium channel can be opened. But being a pacemaker cell, this cell must have a unique characteristic, that is automaticity, being able to generate its own action potential without help from adjacent cell. So how is this possible? The answer is right here, our hero called the Mr. ATPase. What did he do? He did nothing except becoming just a little bit tired. So what happens when Mr. ATPase got tired? He used to push 3 sodium out with every 2 potassium going in. Remember, he is the reason sodium and potassium concentration gradient exists in the first place. What if he skips work? Let's put a mathematical representation to our situation. to see what happens when he is doing his job and when he is not. Positive and negative denotes a difference in direction. Let's say we use positive to denote going extracellular and negative for intracellular. So we have 3 sodium going extracellular and 2 potassium intracellular when he is doing his job, right? Well, in terms of electrical gradient, regardless of what ions it is, what is important is its charges because that influences the electrical gradient. Both are positively charged ions, so let's put that into the formula. Now, a simple derivation would help us to arrive at one extra positive ion extracellularly with each sodium-potassium ATPase pump. That is not surprising because we know that our cells are negatively charged. Now, if he does not do his work, a simple logic would tell us the reverse thing would happen, right? So 3 sodium will not be able to go out, they stay intracellular, and 2 potassiums not going in, stay extracellular. Replace them with charges because that's what's matter to us. So we will have one extra positive ion intracellular each time he doesn't do his work. So simply, what will happen is our membrane will become less negative over time. That is why cardiac pacemaker cell RMP are unstable compared to other cells. You can imagine that other cell ATPases are strong and buff, unlike our ATPase in cardiac pacemaker cell. The steady increase of positive charge intracellular enabled its voltage-gated calcium channel to open. There are some differences between voltage-gated sodium and calcium. Previously, we have seen that sodium requires 55 mV for its gate to be open. Calcium gate, however, requires a less negative membrane potential around 40 mV. And that's the first. Secondly, you may wonder how does sodium cause this steep increase of voltage in a shorter time compared to calcium, which has a more gradual increase. Calcium are similar to sodium in terms of the direction of their gradient because they are high in amount extracellular and low intracellular. These gradients are maintained by calcium pumps similar to how sodium-potassium ATPase function. So at rest, the force of its concentration gradient pushes them into the cell. At the same time, the negative membrane pulls them in the same direction. During depolarization, the concentration gradient is maintained, but electrically they are pushed outwards since positive against positive. Calcium concentration gradients are far larger compared to sodium. At RMP, concentration of calcium outside the cell is 2.5 but only 0.0001 inside the cell. Similarly, depolarization won't change its direction of concentration gradient. But the point is, it is 25,000 in 1 in ratio. In comparison to sodium, the ratio is only about 7.25 to 1. So the difference in gradient suggests that it has quote-unquote higher potential than that of sodium, right? This is reflected by its equilibrium potential. It requires a massive 134 millivolts so that the amount of its net movement is zero. You would expect that the graph will overshoot beyond sodium and even steeper. But all of these are not the case simply because of the gates that holding the calcium. The analogy can be represented by these two doors. Imagine that initially both these two doors are closed. At one door we have lots and lots of sodium ions waiting to cross to the other side, and at another we have calcium ions. But once the door is activated, in a split of second the door holding the sodium ions widely opens, allowing lots and lots of sodium ions to pass through at the same time, whereas the door that holding the calcium ions opens very slowly and slightly, allowing only a few to pass. And before it even fully opens, voltage-gated potassium channel open, causing escape of potassium ions out of the cell while calcium slowly enters. And as the calcium channel closes, the membrane potential plunges down as what occur in nerve cell, back to its RMP at around negative 60 mV. Our normal cardiac pacemaker cell is the SA node. But does other cell have such automaticity other than SA node? Well, actually there are. They are called the ectopic pacemaker. These include the AV node and the Purkinje fibers. Myocyte cell, such as the atrial or ventricular cell, has a more stable RMP. However, if damage, for example, due to ischemic injury, can result in unstable RMP, which makes it to have its own rhythmic automaticity as well. But if AV node and Purkinje fibers can generate its own action potential even without injury, then why they are not our pacemaker? Let's look at how they differ from each other. They exhibit a rather similar graph of action potential with only a very slight difference. That is, what we call the rate of spontaneous depolarization. Let's look at the red lines showing their unstable RMP. SA node has the steepest red line, whereas Purkinje fibers has the least. If we put a reference point, let's say between the joining of the orange and blue line for each, you can see that due to the shorter time for spontaneous depolarization to take place in SA node, it enables it to has a faster rate. It completed 4 cycles of action potential before AV node and Purkinje fibers. In fact, SA node excites at a rate of 70 to 80 per minute, whereas 40 to 60 for AV node and 15 to 40 for Purkinje fibers. Thus, these automatically make SA node the pacemaker. AV node and Purkinje fibers wouldn't be able to be the main source to generate action potential to the heart, simply because they are not fast enough and they are already in a refractory period when they tried. But let's say the SA node is injured due to, for example, a block to its blood supply from the right coronary artery commonly. The next fastest cell will be the new heart pacemaker. Lastly, let's look at our cardiac myocyte cells. It has all 3 channels, a stable and more negative RMP. Depolarization from adjacent cell causes the local potential and leads to the opening of fast sodium channel. But after it closes, it did not plunge downward because it also has the calcium channel leading to this plateau. And the rest are more or less the same for each cell. We can divide the phases of cardiac myocyte action potential into 5. Phase 0 indicates depolarization, Phase 1 for initial repolarization, Phase 2 for the plateau, Phase 3 for rapid repolarization, and Phase 4 for resting membrane potential. In comparison to this, cardiac pacemaker cell only has 3. It has depolarization, which is phase 0, followed by rapid repolarization, which is phase 3, and lastly RMP, which is phase 4. That's it for cellular electrophysiology. For the next video, we are going to learn about the conduction system of the heart. If you are interested in other ongoing series such as Human Anatomy According to Body System, you can click on the link here or through the description down below. If this video proved useful, hit the like button and share them with friends and family. Subscribe this channel for future video. Thank you for watching. Bye bye.